Let's go ahead and walk through this study set. And this question, actually, I think it's the same question or similar to one that was in our notes. There's two different ways you can do it. So you can always go through steps where you do PV equals nRT. You solve for the moles of the SiH4. Then you do your mole to mole ratio, right? I did it actually a different way, and I'll show you that in a minute. So there is always more than one way, but so you would have, then you'd have your second step would be this, and then your third step is you would do PV equals nRT again, and you'll get my answer. The way I did it is I did P1, V1, N1, T1, and this was all, my ones were all for the SiH4, and I set that equal to P2, V2 over N2, T2. So you can do that with a balanced equation. These will all be for oxygen. So my P1 was the 345 torr, 5.43 liters. And then I do 1 mole. And the 1 mole is coming from the balanced equation. And then the T1 is whatever that is, 296 Kelvin. Right, and we'd have to rearrange. So my N2, these two would now move to the top, right? We'd cross multiply, would be the 2 moles of oxygen, which is from the balanced equation times its temperature, which is, sorry, 273, so 305 Kelvin divided by the pressure, so 654. 654 millimeters of mercury is the same as torr. So millimeters of mercury and torr are interchangeable. The advantage of this way is it's one step. There's a lot of numbers to rearrange, and you don't have to switch to ATMs because the torr and the millimeters of mercury are the same. If you use R, you would have to switch to ATMs. If you use R, I think when we went through this, this comes out as 0.101 mole of SiH4, and then you just keep going from there. It's fine to do it either way. If you, again, you're going to always state your formula, and then show when you, if you do it with this one, you would have to state just not 1 mole and 2 moles, but 1 mole of SiH4. So remember that when working with balanced equations. If you break it into the 3 steps, you need to number your steps so that it's logical and I can follow it. So, all right, number 10. These are all the numbers for CO2. So if you know, since we're solving for the solid, our first step is going to be PV equals nRT. Sometimes, and I think that happens on the worksheet, I actually give you the mass of the solid or the volume of the liquid or something. And so your first step is you have to go from that mass or volume of the solid or liquid and change it to moles of the gas. So gas laws use moles, not mass. And so keep that in mind. That's actually the hardest thing to get. And so several people were here early. This is a harder worksheet, and you should be grateful for that. Because if I push you a little bit on the worksheet, it will make your exam, the celebration next Tuesday, that much better and stuff. So just make sure you study. There is also more problem solving on the lab if you want to try those. They are more challenging. I'm not planning to do office hours on Saturday unless somebody feels they need them. Just send me an email or talk to me tonight. I need a break from Zoom too, but you can send me an email always and a picture and ask me, hey, this is what, because there's some people who do that. They take a picture and say, where am I missing? What step am I'm not getting something here. All right, so we would go through this. So the pressure, you do need to change it to ATM. So you can just, dividing by the 760. The volume is in liters. So a couple of you on the previous worksheet, your answers were off because you were in milliliters. So you have to be in liters. A reminder, a liter is the same as a cubic decimeter. So that will be helpful on the worksheet. I think the third question, I start you with cubic feet. So you just have to change it to cubic decimeters. And then that's your liters. Divided by R times the temperature. And so that's going to be 295. Yeah. That will give you moles. And so hold on. That is always gas laws. This is moles of CO2 because that's our gas that we're dealing with, which I don't actually have the number. I did this all in one setup, but this is your moles of CO2. And so then you would take that number. It's really funny. That would be your moles of CO2. And so you can do arrows, or this is step 1 and this is step 2, that you would take those moles of CO2 and you would do your mole to mole ratio. So 2 moles of CO2 to 4 moles of KO2. And then 1 mole is 71.1 grams. So make sure for your celebration you have your periodic table handy. I mean, I don't know how you could do any of this without that. And you should get my answer, the 40.0 grams. So questions with that? And again, I do it all in one flow setup, so I don't have all my intermediate steps for some reason on this. All right, this next one is often a challenge for students because there's 2 pressures and volumes given and 1 temperature. But for the first one, you're just going to do PV equals nRT, the 12.3 liters, the 1.00001 ATMs, and then R times our temperature, so 293 Kelvin. And that will give you, so 294, sorry. That will give you the moles. And then once you get to moles, you would then multiply by 0.03 grams per mole because it's helium, for helium. And that will give you the 2.04. PV equals nRT. If you have a balanced equation, like on the first 2, you're going to be using PV equals nRT. We don't use the PM equals DRT. There, you can use it, but really I just save that if the question point blank says what's the density or what's the molar mass. It's just a rearrangement of PV equals nRT. On this one, what is the final? So you could have done, I guess you could have done PM equals DRT, but the partial pressure, this is P1 V1 equals P2 V2. This is the one I know from being in person for 2 decades that everybody always struggled with because they're like, but I have 2 of everything. This is your piece that's unknown. So you're going to take your original pressure and volume, so the 1.0001 ATMs, the 12.3 liters, and we would divide by the 23.4 liters. So we're starting with this much helium. So those are our original numbers for helium. The gas expands when you give it a chance, so it's going to expand, and so that makes sense. The pressure, right, started around 760 and it's now about half that. And so if you did it in ATMs, it would be 0.526 ATMs. I didn't specify units, so either answer is fine. However, switching to torrs does have an advantage because here the total pressure is the sum of the 2 partial pressures. So if we have our total, and you could do this in ATMs or you could do it in torr. I just did it in torr. Our total was 789 torr. And so then I just subtract the 399 torr, which was the helium. So this was my total minus the helium, and that would equal the pressure of the oxygen. And again, you can do it in ATMs or torr. You just have to have consistent units. And so it's the idea that pressures you can add up, moles you can add up also, but volumes you have to be careful of because they'll just expand to take up whatever space there is. All right, so the good news is it is math. So you get, it's just crunching numbers. So on your celebration, which is Tuesday, this is like the first 2 pages is just crunching numbers. So you want to do your worksheets. Everything's due by Tuesday, so your late stuff. And I'll be here Tuesday at 5 if you have questions. And because of the math, you get more time on this celebration. All right, but there is a lot of theory stuff, and that's why we're going to do practice after this. So liquids was all theory stuff. There was a little bit of math. Solids had math, but you guys do fine. You will do fine because you have your notes. All right. So we have these 3 samples. So just a reminder what STP is, right? So that is 0 Celsius. We'll just keep them all in Celsius. Oh, that was the other thing to remind you. You have to always be in Kelvin, no matter what, with gas laws. Why?
Because of the value of R, it's in Kelvin. So
that is one reason, yes. So if you're using R, you have to be in Kelvin, you have to be in ATMs, you have to be in liters. But even if you are doing the ratio, the P1 V1 over T1, you have to be in Kelvin. Why? Like on this one that I did, I kept it in torr because I didn't use R. So why do you have to always be in Kelvin no matter what? Anybody remember?
The motion.
Yeah, so gases are all about chaos, motion, giggles and jiggles. So Tristan, I have to say that you didn't do the giggles and jiggles, so you won't be on the plane giggling and jiggling for a couple hours, flying, and with all those people in the aren't whatever in the reserves, there's no giggling and jiggling. So anyway, just the thought of that made me giggle and jiggle. So 0 Celsius, I'm not doing any math here, I'm just comparing them, so I'll keep it in the same units. And standard pressure is 760 millimeters of mercury, 1 ATM. So that's kind of ingrained with you forever. When you do physics, a lot of you will be doing physics next year. You do gas laws, so that's good news. When you get to gas laws, you're like, you got it. They use pascals, that's the standard unit, or kilopascals, and there's a reason. We just use ATMs, I think, because 1 ATM is standard, it makes it easy. So which has the largest number of gas particles? And this is going to be helium. And if you think about it as PV equals nRT, N is going to tell us how many moles. So the number of particles is related to the number of moles. So whichever one is going to have the most moles. And again, there shouldn't be calculations here. It's an explanation. So from PV equals nRT, that if the one that has the most moles, the temperatures are not a big difference. The pressure, the one with the greatest pressure, so the highest pressure, most collisions, is going to have the most moles. You could also do it from temperature, so high pressure, which means most, collisions, would mean that you have more moles. You can also say a low temperature. We just have 2 things with the lowest temperature. Low temperature means they're in the same space. They're moving slower. Temperature and moles are always indirectly related. I briefly talked about that the other day. It just has to do with how algebra works out. If they're on the same side of the equation, if one goes up, the other goes down. This is actually a harder question than what I usually give you because there's 2 variables happening here. But the change in temperature is actually very small because once you change it to Kelvin, that factors in. If they're on opposite sides of the equation, they'll have a direct relationship. So temperature means that a lower kinetic energy in the same space would mean that you have more moles. So the helium is the largest one there. Again, the pressure is the biggest piece there. The highest kinetic energy, it's always average because nothing's ever exactly the same. Kinetic energy is directly related to temperature. So the higher the kinetic energy is if you have the highest temperature, the most giggles. And so only one of them had a high temperature, and that would be neon. All right, if you were asked RMS speed, that would be a difficult one with this one because there's two variables, and so I wanted to mention that. So it's always called RMS speed because there's two factors. As you increase the temperature, you increase the velocity, so the speed. So we would want to go with neon. However, the smaller molar mass also increases the speed, which would put it with helium. And so then we'd have to plug it into a formula to figure out which one it would be, since there's two variables there. So again, usually if you're asked that, they're either all at the same temperature or it's just one thing at different, or it'd be like a true false, like at the bottom. That's why that question's not on here, because I didn't want to use that formula. I showed that formula in the notes, but you take physics, you gotta use that maybe. All right, which one has the most collisions? The highest pressure is highest collisions, and that would be the helium. So again, pressure is collisions, temperature is giggles and jiggles and wiggles. Oh my, and volume is how much space, moles is how many particles you have. And density is how much is packed into a space. 13, sorry, I have to make a thing. So flask A is hydrogen, 0 Celsius, 1 ATM. I'm always amazed because people turn in their tests and they'll just have answers, and I have to always write down. So in B, their volume is equal. It is CO2 at 25 Celsius and 2 ATMs. So the average kinetic energy is the higher temperature, and so that would be the CO2. The speed, so it is actually the hydrogen, and it is because the difference in size is quite significant here, and so smaller size is going to be faster. All right, number of molecules, it's going to be the CO2, and that is because pressure, the change in pressure is significant. So since you double the pressure, which means more collisions, that must be due to double the moles, or close to that. There is a change in temperature here. This kind of goes back with B also, why I didn't look at the temperature. If you change it to Kelvin, it's 273 and 298. That's like a 10% difference. It's a really small difference. This is a doubling. It's 100% more. So the change in pressure, everything is proportional. The change in pressure is our biggest difference here. The change in temperature is really small. We'd have to almost double the Kelvin temperature, so be it like 200 Celsius. Then we'd start seeing quite a bit more giggles and jiggles because you're really getting it moving. All right, the mass of the gas is, so this is CO2. And the mass is the CO2. Since you have more moles and has a greater molar mass. So this one must have more moles due to the more collisions. Times a higher molar mass. That means it's definitely going to have a greater grams. All right. On this one, we have nitrogen and argon. And their masses are the same. And their volume is the same. And their temperature is the same. So the answers for every single one of these is nitrogen. So nitrogen wins every single one of them. The one with the more molecules, that's if the mass is given. If they're the same mass, I have to think. Oh, sorry. If you figure out from the periodic table, this is 28 grams per mole, and argon is 40 grams per mole. So the one with the lower molar mass, if volume and temperature, okay, this must have the more moles, which means the more molecules, so nitrogen. So if you're taking a given mass and then you're dividing, right? So if you have like, say 1 gram and you're dividing by so many grams per mole, the smaller the number you divide by, the larger your answer will be. These are logic questions, and some students are much better at logic questions than others. They're really good. I was always, I don't know why. Keep in mind, this is one, like, this will be just a few questions on the test. So do the best you can and just keep moving on. So you're given more time than they would be in person, partly because of distractions, to give you the time to print and to scan. But you shouldn't take the full 3 hours. You really should all be able to finish it in 2 hours, but you're given the extra time. And also so you can come on to Zoom, and because who knows, things happen. The greater pressure, so the volume and temperature are the same, so we're looking at the moles. More moles means more collision. And so that goes with A, so it's going to be the nitrogen. Whichever one had more moles is going to have more collision, since you have the same kinetic energies and space. A question that Major had asked me like a week ago when we started on gas laws, he said, would you need to put this piece in there? It is actually a good idea to mention that because the other factors are the same, because sometimes like up here, we had 2 pieces of information. And so the one is usually much more significant. All right. Since they're at the same temperature, so same temperature, the smaller one, the lower molar mass, is going to have the greater speed. And so that is nitrogen. So even if you forgot that nitrogen was a diatomic, it was still the smaller one. But do remember diatomics, the nitrogen, oxygen, hydrogen, chlorine, and fluorine. So when they're talking about just one of them, they're diatomics. And then which one collides more frequently? That's the one with the higher pressure. So B and D really go together. So that is nitrogen. I thought that we're going to add a question here. We're going to ask E, so somebody can get on the board. Which one has the higher density? So I've had this question on test, and what a lot of students do is they say, okay, I can do this with PM equals DRT. So this would be one where argon finally wins. The higher molar mass will have the higher density, but they're wrong. It's actually neither. They have the same density. Why?
Same volume and same mass.
Yeah, so if the mass and the volume are the same, your density didn't change. It's the pressure and the molar mass are our 2 variables that are different in this one. All right, last one. All right. So which ones are wrong? So this is like true, false, and then we're just gonna give a quick explanation why. So yeah, higher temperature, that's okay. That one's correct. So as you increase the temperature, you're increasing the jiggles, right? And so everybody's jiggling, and so everything's moving faster. So temperature is kinetic energy, is movement. On B, that goes with this. So hydrogen is, as you decrease the molar mass, you increase the speed, the velocity, whatever term you want to use there. So hydrogen, even though it's a diatomic, it's still the smallest. So that one's was okay. That one was correct. C and D are the ones that are wrong. And diffusion occurs faster at a low pressure. So diffusion is that we're dispersing it, and so a higher pressure, you're going to push them apart. You can also go with that a higher pressure would mean you have a higher temperature too, that they're going to be proportional, but it logically makes sense that pressure is all about collisions. So if you have a higher number of collisions, you're definitely going to have that you're pushing them apart. So everything's getting dispersed. It doesn't, yeah. So it's going to take up more space. It wants to spread out because they don't want to have collisions. Gases do not like a high pressure. They really don't like pressure at all. Same like us. All right. The rate is proportional to molar mass, and it's indirectly. So as one goes up, the other goes down. So that's why that one was incorrect. And that's it, unless there's a question. If there's no question, I'm going to stop and move on